So this is section 6.4 about logarithmic functions. So a logarithm is the inverse of an exponential function. If you remember from 6.2, we talked about inverse functions and how you can find them by switching x and y. Well, if you do that with an exponential, you get a logarithm. And so here's our kind of basic steps. The first step, we replaced f of x with y, so we had y equals b raised to the x power. Our second step, we switched x and y, so we switched them around. X equals b raised to the y power. And then the last step is to solve for y. Well, to get y by itself, you have to get rid of this exponential. You have to get rid of this b. And so to do that, we use a logarithm that has the same base. And so we end up with y equals log base b of x. Now, these logarithms do have some properties associated with them. First off, x, this thing that's inside the logarithm, has to be greater than 0, has to be positive. B, the little base number down here, has to be greater than 0 and cannot equal 1. Okay. So those are some stipulations here on our logarithm. Now, you can actually change back and forth between exponential and logarithmic form as long as you remember kind of where things go. So if you have a logarithm, y equals log base b of x, this y was originally the exponent over here. This b was originally the base, and then this x that's inside the logarithm was originally the solution. So you can kind of go back and forth between the two. You can take something that's written with logarithms and rewrite it as exponential, or you can take something that's exponential and you can rewrite it as a logarithm. So you can kind of go back and forth between the two forms. And so that's what we're going to do here in example 1 and 2, is we're just going to kind of go back and forth between the two forms. So example 1 asks us to write each equation in its equivalent exponential form. So we have 2 equals log base 5 of x. So the first thing to do is identify your base. In this case, our base is 5, so we write that down. Then we need our exponent. In a logarithm, the exponent is the thing over on the other side of the equal sign. So our exponent is equal to 2. And then we write equals. And then the thing inside the logarithm is your solution. So that's my x. And so there we go. There it is in exponential form. All right. On b, we got 3 equals log base b of 64. Again, identify your base first. My base is b. Then get your exponent. My exponent is 3 equals, my solution on the inside of the logarithm is 64. And then letter C, we got log base 3 of 7 equals y. What's my base? My base is 3. What's my exponent? My exponent's on the other side of the equal sign, so it's y equals, and my solution is inside the logarithm, so it equals 7. Here we go. We took 3 logarithms, rewrote them as exponentials. All right. Here in example 2, we're going to kind of go the opposite way. We're going to take something that's written as an exponential and rewrite it as a logarithm. So first off, I'm going to write log. Then I'm going to write down my base. Well, if I have 12 squared equals x, what's the base? Well, the base is the thing that has the exponent, so the base here is 12. Now, inside this logarithm, we write our solution. Our solution was x equals, and on the other side of the equal sign, we write our exponent, which was 2. So log base 12 of x equals 2. All right. Next one, we got b to the third equals 8. So again, we're going to start by writing log. Then we're going to write down our base. Our base in this case is b. And then we're going to write down our solution, which was 8, equals, and then we're going to write down our exponent, 3. So log base b of 8 equals 3. All right, letter C. We got e raised to the y power equals 9. So first thing we're going to do is we're going to write log. Then we're going to write our base. Our base this time is e. And then next to it is our log. We're going to write our solution, which was 9, equals our exponent, which was y. Now here's the thing with this one. This log base e actually has a special name. it's actually called an ln, a natural log. So we could actually write this as ln of 9 equals y. It's kind of a math shorthand. ln stands for log base e. And so we don't usually write out log base e. It's not mathematically incorrect to write log base e. It's just we don't usually do it. We usually write ln instead. Okay? So our next thing asks us to evaluate some logarithms. Now, we're not going to use a calculator yet. I'll show you in just a minute how to do a calculator. But for right now, we're going to see if we can evaluate these without a calculator. So I have log base 2 of 16. Now, I don't know what that equals, so I'm going to say, hey, let's say that equals x. I don't know what it is yet, so we'll just call it x. So what we're going to do is we're going to take this logarithm, and we're going to rewrite it as an exponential. So what's my base? My base is 2. What's my exponent? Well, it's over here on the side of the equal sign, so it's x equals, and what's my solution? My solution is 16. And now what we have is an exponential equation. And back in 6.3, we learned how to solve these exponential equations. We solved them by getting a common base. So what is a common base for 2 and 16? It's 2. So I can leave this left-hand side as 2 raised to the x, and I can rewrite this right-hand side, 16, as 2 to the 4th power. So 2 to the x equals 2 to the 4th, so we know x has to equal 4. And since x is the answer to this logarithm equals 4. Okay. Alright, same kind of thing with letter b here. We have log base 7 of 1 over 49. I don't know what that equals, so I'm just going to say, hey, it equals x. And now that we have it written as an equation, we can convert it into an exponential. Our base is 7. Our exponent is x. And it equals 1 over 49. Oops. All right. So now I need to figure out, is there a common base for 7 and 49? And there is. It's 7. So I can leave this as 7 to the x. And this one I can rewrite as 1 over 7 squared. Because 49 is 7 squared. But here's the thing. If you have a power in the bottom of a fraction, what was it originally? It was originally a negative exponent. So this is really 7 raised to the x equals 7 raised to the negative 2 power. And then if that's true, if 7 raised to the x equals 7 raised to the negative 2, x has to equal negative 2. And since x is the answer for this logarithm, we know this logarithm equals negative 2. Alright, letter C, we got log base 25 of 5. Again, I don't know what this equals, so I'm going to say, hey, let's say it equals x. Then we'll rewrite it as an exponential. Our base this time is 25. Our exponent is x, and it equals 5. We want to find a common base. What is a common base for 25 and 5? The common base is 5. So we can rewrite 25 as 5 squared, getting raised to the x. And then this one we can just leave alone as 5. Now what power is on this 5 technically? Yeah, technically it's a 1. Over here on the left-hand side, we have a power getting raised to a power. When you have a power raised to a power, you multiply the powers. So you're going to have 5 raised to the 2x power equals 5 raised to the first. At that point, we can now set the exponents equal to each other and say 2x equals 1. And then we can divide the 2 across and say x equals 1/2. Now, because that equals 1/2, again, that's the answer for this logarithm. That's the value of that logarithm. Okay? So that's how we can evaluate some logarithms by hand. Now, there are other logarithms that we can't do by hand that we have to use a calculator for because they don't come out exact. And I'll show you how to do those in just a little bit. But next, we're going to talk about some properties of logarithms. The first two are two basic ones. If you have log base b of b, it always equals 1. So if this number is b and this number is b, they more or less cancel each other out and you just get a 1. This comes from the fact that b raised to the first power always equals b. It's one of those things. Similarly, log base b of 1 always equals 0. It doesn't matter what number b is here. If you have a 1 inside your logarithm, it's always going to equal 0. And again, the reasoning behind it is exponents. B raised to the 0 power always equals 1. So if we apply those properties here, we have log base 7 of 7. These are the same, and so that logarithm is just going to equal 1. Over here, log base 5 of 1. Because this is a 1 inside of here, it's going to equal 0. Pretty straightforward. Now, remember that logarithms and exponentials are inverses, which means they undo each other. Remember from 6.2 when we talked about inverses, that when you take a function and you plug it into its inverse, the function and the inverse cancel out and you just get the variable x. And that works for logarithms and exponentials as well. So if you take an exponential and you plug it into your logarithm, the logarithm and the exponential cancel out and you just get x. Similarly, if you take a logarithm and you plug it into an exponential, the exponential and the logarithm cancel each other out and you end up with just x. So because exponential functions and logarithmic functions are inverses of each other, they cancel each other out. And so we can kind of apply that here in example 5. It asks us to evaluate log base 4 of 4 to the 5th power. This is a logarithm with a base 4. This is an exponential with a base 4, so they will cancel each other out. And all that gets left over is that exponent at 5. Pretty straightforward. Same kind of thing over here with number 6. We have, letter B. We have 6 raised to the log base 6 of 9. Okay. This is an exponential base 6. This is a log base 6. The exponential base 6 and the log base 6 cancel each other out. And so all we're left over with is 9. Now, one thing to stress is they have to have the same base. Like, this had to be base 4 and this is base 4 for it to cancel out. This is 6 and this is base 6. Those will cancel out. If I had something like log base 4 of 3 to the 5th, they wouldn't cancel out because this is a base 4, but this is a base 3. And so they wouldn't cancel. So just bear that in mind. They have to have the same base number if they're going to cancel. The next thing we're going to talk about is graphing. To obtain the graph of a logarithmic function, you actually first off have to get the graph of the exponential function, b raised to the x. Once you have that graph, then all you have to do is switch the x and y, because remember they're inverses, and when you have inverses, x's and y's switch. Now here are a couple of notes about logarithmic graphs. The domain of an untransformed logarithm is always going to be 0 to infinity. The graph will pass through the point 1, 0 every single time, and again, unless there's a transformation. And that point is the x-intercept. And again, unless there's a transformation, there should be no y-intercept. The graph will also go through the point b, 1, just because log base b of b has to equal 1. So that point always has to be there. Now, if your base number is 1, your graph, or is greater than 1, your graph is going to be increasing and going to the right. So it's going to look kind of like this. But if your base number is between 0 and 1, it's going to be kind of going like this. So just kind of understand that, beware of that. And the last thing, the graph is going to approach but not touch the x-axis. Not the x-axis, sorry, the y-axis. The y-axis is a vertical asymptote here. That's how they work with logarithms. They always have a vertical asymptote. So let's look at an example of this. I'm actually going to, oops, I don't want that to be dotted. I'm actually going to make my x-axis be all the way down here at the bottom. No, I won't. As I go back, I'll make it go up one. I'll make this be my x-axis. And then that'll be my y-axis. Alright, so our example here asks us to graph a function f of x equals 2 raised to the x power, and g of x equals log base 2 of x. So these two are inverses of each other because they do have the same base. So we're going to start by graphing 2 raised to the x. Now this is one that we can actually do by ourselves without a calculator or anything like that, just by plugging in. Okay. When we plug in -3, remember the negative flips it, so you're going to have 1 over 8. When you plug in 2, the negative 2, the negative flips it, so you're going to end up with 1 over 4. When you plug in -1, the negative flips it, so you have 1 over 2. When you plug in 0, 2 to the 0 power is 1. When you plug in 1, 2 to the first power is 2. When you plug in 2, 2 to the second power is 4. And when you plug in 3, 2 to the third power is 8. And so if we kind of plot those points, oh, you know what, I actually went up too far, didn't I? So at -3, it should be at 1/8. -2, it should be at 1/4. -1, it should be at 1/2. 0, it's at 1. 1, it's at 2. 2, it's at 4. And then 8 would be just a little bit off the graph. Okay, so that would be our graph of this function. Now we're going to do log base 2 of x. Now for log base 2 of x, all we have to do is just switch the x's and y's around. So we'll have 1/8 -3, 1/4 -2, 1/2 -1, 1 0, 2 1, 4 2, and 8 3. And so then we plot those. So at 1/8, it's going to be at -3, so it's going to be way down here somewhere. At 1/4, it's at -2. Let's say like right there. At 1/2, it's at -1. At 1, it's at 0. At 2, it's at 1. At 4, it's at 2. And then 8 3 is going to be way over here somewhere. So there's the graph of our logarithm function. Again, all you have to do is switch x's and y's. So that's how you do logarithm graphs. You start by getting the point for your exponential that has the same base, and then you switch x and y to get a logarithm. Now, you can do transformations of logarithms just like you do transformations of other functions. They're not too bad. If you have a plus or minus c outside of the logarithm, then it shifts the graph up or down c units. So if it's plus c, it shifts it up c. If it's minus c, it shifts it down c. If you have a plus or minus c inside the logarithm, inside here with the x, then that's going to shift your graph left or right. Please remember, though, that when things affect x, it's opposite operation, so it's going to be the opposite of what you think. So plus c will actually shift it to the left, minus c will shift it to the right. If you have a negative outside the logarithm in the front, it will reflect the graph across the x-axis. If you have a negative inside the logarithm, then that's going to reflect it across the y-axis. A number c multiplied out front of the logarithm will cause a vertical stretch or shrink. It will be a vertical stretch if the c is bigger than 1, a vertical shrink if the c is between 0 and 1. And then, if you have a number c being multiplied inside the parentheses, inside the logarithm, then that's going to cause a horizontal stretch or a horizontal shrink. Remember, it's opposite of what you would expect. So if the c is bigger than 1, it will actually shrink the graph. It will divide it by that number c. And if c is between 0 and 1, it will actually stretch the graph when it divides by that number. So with these, when you do transformations of these graphs, basically what you do is you start with the exponential, like 2 raised to the x power. Then you switch x and y to get your logarithm, and then you apply your transformation. So it's kind of a 3-step thing. Find exponential, find logarithm, apply transformation. Alright, moving away from graphing, let's talk about domain of logarithms. The domain of a logarithm is if you have a log base b of g raised to the x, the domain is all x's where g of x is greater than 0. So whatever is inside this logarithm has to be greater than 0. And so if you see example 7 here, it asks us to find the domain of f of x equals log base 4 of x plus 3. So to find the domain, we take what's inside the logarithm, we take the x plus 3, and we say it has to be greater than 0. Solve it for x, so move the 3 over, x has to be greater than negative 3. Now if they want that in interval notation, then we can say this goes from negative 3 not included on to infinity, because infinity is greater than negative 3. So there is our domain for that logarithm. Alright, so now we're going to talk a little bit about 2 special types of logs, one of which we've mentioned already, and one that we haven't. Okay. So there are 2 special types of logs. The first one is called a common log. A common log is a logarithm that has a base number of 10. This one is very common because our number system is in base 10, and so we use 10 as our counting number, and that's why that logarithm is common. So if you look at your calculator, you'll probably see a log button. That log button is the common log. So like if I look at my calculator, I have this log button here next to number 7. That log button is my common log. Now, one cool thing about this is that there is a formula called the change of base formula that will allow you to take a logarithm that is not in base 10 and rewrite it into base 10. So like, let's say we have log base 5 of 2. My calculator doesn't have a log base 5, but it does have a log base 10. And so I can actually take this log base 5 of 2 and I can rewrite it as log of 2 over log of 5. Basically log of the number inside and then over log of the base. And those are both in base 10. And I can just go to my calculator and I can actually do it. So I can be like, hey, I'm going to do log of 2 divided by log of 5. And there's my answer. And that would be the same thing I would get if I did log base 5 of 2. So that's kind of a cool thing for calculators, is that you have this formula called change of base, which allows you to change it into base 10 and actually put it in your calculator. Alright. The other special logarithm is the one we talked about earlier at the very beginning. This is the logarithm with a base e, called the natural logarithm. With natural logarithms, we use ln to represent them, ln. And most calculators have a button for that as well. So if you look at my calculator here next to number 4, there's an ln button. That ln is for the natural log. Okay, and that's a log with a base e. Now, logarithms, natural logarithms, are the same as any other kind of logarithm when it comes to domain. Whatever is inside the natural log has to be bigger than 0. It's just one of those things. And so if we look here, example 8 asks us to define the domain of these natural logs. So for this one, we would say 3 minus x has to be greater than 0. Move the 3 over, so negative x has to be greater than negative 3. Then we would divide both sides by negative 1. But remember, when you divide by a negative, the inequality flips, so it's going to be this now. And then negative x divided by negative 1 is x. Negative 3 divided by negative 1 is 3. So x has to be less than 3. If we wrote that in interval notation, that would be negative infinity to 3 with the 3 excluded. Because negative infinity is less than 3. For the letter b here, h of x equals ln of x minus 3 squared. So for our domain, we would say x minus 3 squared has to be greater than 0. Take the square root on both sides. X minus 3 has to be greater than 0. Add the 3 across, you get x has to be greater than 3. Or if we wrote that in interval notation, this time it would be 3 to infinity. So that way we go greater than 3. So the domains work pretty much the same way with natural logs. There's no real secrets there or anything or tricks. Alright, next thing we're going to look at is solving logarithmic equations. There are several ways we can solve logarithmic equations, but one way we're going to look at today is rewriting them into exponential form. Many times you can rewrite a logarithm back into exponential form and then solve it from there, and that is really convenient. Now, one thing I have to warn you about is with logarithms, you do need to check your answers, because whatever answer you get, you need to make sure that it doesn't make the inside of the logarithm a negative number, because the inside of the logarithm always has to be positive, and so you have to actually check your answers and make sure that that's true. Alright, so let's look at example 9 here. It asks us to solve these two equations. Our first one we have a, which is log base 3 of 4x minus 7 equals 2. So the first thing we'll do is we'll rewrite it as an exponential. My base number is 3. My exponent is 2. And it equals the stuff inside here, which is 4x minus 7. All right, 3 squared is 9. So 9 equals 4x minus 7. Add the 7 across. 16 equals 4x. Divide both sides by 4, we get x equals. And again, you want to check yourself, make sure it's okay. So if we take 4 and plug it in, 4 times 4 is 16. 16 minus 7 is 9. 9 is a positive number, so that's okay. That answer is fine. Alright, letter B here. We got log base x of 64 equals 2. So we're going to rewrite it as an exponential. My base number is x. My exponent is 2. And it equals 64. So we have x squared equals 64. To solve this, we would take the square root. And so we would get x equals plus or minus 8. Then again, you have to check your answers. When I plug in 8, it works fine. That's just going to be a positive 8 right there. It'll be great. But when you take a negative 8 and try to plug it in, that'll be a negative number there, and you can't have that. It has to be a positive number. So only x equals 8 works. X equals negative 8 will not work there. Number 10, we have asked us to solve here e to the 2x equals 5. How we're going to do this is we're going to rewrite this exponential as a logarithm. So we're going to write log, what is the base of our exponential? It's base e. What was the solution? The solution was 5 equals, what's the exponent? 2x. Now remember, we usually don't write log base e. Usually what we do is we write ln. So this is really ln of 5 equals 2x. And then we could divide both sides by 2. So x equals ln of 5 over 2. Or if we want a decimal, we can go here to our calculator and do ln of 5, close the parentheses for the ln, and then divide by 2. So 0.805 if I go to 3 decimals. Now, this first one's the more preferred one because it's exact. But that one's not bad. It's an approximation, but it's not too bad. Okay. So sometimes you can solve exponential equations by rewriting them as logarithms too, and it's not too bad. All right, I think we have one last thing we're going to look at. Yep. So our last thing is a word problem involving exponentials and logarithms, which is not too bad. It says, recent medical research suggests that the relative risk R of having an accident while driving a car under the influence can be modeled by R equals e to the kx, where x is the percent concentration of alcohol in the bloodstream, and k is a constant. Part A says, research indicates that the relative risk of a person having an accident with a blood alcohol concentration of 0.02% is 1.4. Find the constant k in the equation. So they gave us a couple of things. They gave us the percent, which is the x, and they gave us the relative risk, which is the r. So we're just going to plug those into this equation. So 1.4 equals e raised to the k times 0.02. Now, again, to solve this, we need to use logarithms. So we're going to rewrite it as a logarithm. We're going to say log, our base is e, our solution was 1.4, and it equals our exponent, which is k times 0.02. And then we can clean that up a little bit. Log base e is ln, so this is ln of 1.4 equals k times 0.02. And then we can solve for k by dividing the 0.02 across. So we go to our calculator, ln 1.4, close the ln, divided by 0.02, and there's my k. So 16.824. Now here's the thing, I'm not going to use this rounded number when I do subsequent problems. I'm going to use this one that's still in the calculator. I'm going to let it keep all those decimals, so that way my answers stay more accurate. So part B says, using this value of k that we found, what is the relative risk if the concentration is 0.17%? So they've given us an x, and they're asking us, what is the relative risk, or what is R? So we're just going to fill in what we know. We don't know R, that's what they're asking us about. We have E, we know our K, which is at 16.824, and that's getting multiplied by this X, 0.17. And so I'm going to go to my calculator. To do an E, you see it's up here in blue above the ln, so I'm going to do second ln to do my E. And then I'm going to tell it to use this previous answer. So I'm going to say, hey, use that previous answer, the 16.823 blah, 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 and multiply it by 0.17. You can close my parentheses on my E, hit enter, so that's 17.462. Is the relative risk. Okay. All right. Part C says, using the same value of K, what blood alcohol concentration corresponds to a relative risk of 100? So they're asking us what blood alcohol, so what X, and then they've given us a relative risk, so this is our R. We're just going to fill in 100 for R equals E raised to the, whatever that is, what is it, 16.824? And then we don't know x, so we have to leave it as an x up there. Now again, you want to rewrite this as logarithms to help you solve this equation. So we're going to say log, our base is e, inside of it our solution is 100 equals our exponent, which is 16.824x. And then we can rewrite that. Log base e is ln, so this is ln of 100 equals 16.824x. And then we can solve for x by dividing the 16.824 across. Unfortunately, I'm going to have to get that number again, so I'm going to have to say ln of 1.4 divided by 0.02, so that way I have the 16.824 again. And then at that point I can say, okay, let's take ln of 100 and divide it by that unrounded answer. And so there we go, 0.274%. So that's our blood alcohol concentration that would correspond to a relative risk of 100. And then our last part, part D, says, if the law asserts that anyone with a relative risk of 4 or more should not be driving, or should not have driving privileges, at what concentration of alcohol in the bloodstream should a driver be arrested and charged with a DUI? So they've given us another, oh, my mouse is crazy there. They've given us another relative risk, so here they're telling us that R has to equal 4. And so they're asking us to find the what concentration of alcohol. So they're asking us to find the X. So I'm going to fill in 4 for my R equals E raised to the 16.824x. Now this looks a lot like this one. In fact, the only difference is instead of a 100, we have a 4. So we can actually kind of skip down to this step and just say, hey, ln of 4 has to equal 16.824x. And then we can solve that for x. I am going to have to go back and get that number again. So ln of 1.4 divided by 0.02. So that way I have that unrounded number. But this time I'm going to do ln of 4 and I'm going to divide by that number. And so I get 0.082%. So according to this model, if your blood alcohol is 0.082%, and you have a relative risk of 4, and according to the law, that means you should not have driving privileges. According to this model with this particular problem, it's really good on that. So that is it for 6.4. If you have any questions, remember, feel free to email me, especially if they're homework questions, and I can try to help you the best I can.